Hi everyone. Today I want to talk about circular motion. This is going to be a whammy of a video, so buckle in tight. We're talking about linear velocity versus angular velocity. So what do these two things mean? Linear velocity is how we measure linear distance, driving for example. Angular velocity is how circles move over time. Think of revolutions per minute or how fast a bike tire goes around in a circle. Linear velocity is usually measured in, again, things that are in a straight line that we can measure pretty easily. Think miles per hour, feet per second, inches per hour. Dimensional analysis is really big here actually, so we'll get into that later. I told you not to use red. Red's hard to see. Moving on. Something that's measured in a straight line, again. Angular velocity, think of things again like circles, moving around, wheels, revolutions per minute, radians per second, degrees per hour. All things that have some kind of a circular motion. So, let's see where we're going with this. There are a lot of formulas in this video. You might want to write them down. You might want to memorize them. You might want to love them, because they're amazing. Linear velocity, the formula is this. V, for velocity, equals to delta S over delta T. Huh? Delta just stands for the change in something. So in this particular case, linear velocity stands for the change in arc length, which is S, not speed, divided by the change in time, T. Now, from an alternate standpoint, it also means this formula. The change in arc length is going to equal whatever the velocity is times the change in time. So what did I really do here? All I did to the top equation was I multiplied by delta t on both sides to get rid of the denominator. It's exactly the same thing. It's just an alternate way of looking at it. Because sometimes we're going to need to solve for arc length, which we're getting to. Angular velocity, however, we're going to use a brand new letter. That looks like a W. It's not. It's omega, yet another Greek letter. We have to use Greek letters, like theta, to represent the differences between angular velocity and linear velocity. As you can tell, there's nothing really crazy about things that are linear. But the second we go into trigonometry, pre-calculus, things get a little messy. So we're going to use omega as our formula or our variable for angular velocity. Get used to it. For angular velocity, we kind of have the same idea. The formula stands for the change in theta, or the change in the angle, over the change in time. Let's compare the two. In the first one, arc length, something that can be measured linearly. Theta, something that can only be measured from an angle. Linear versus angular. I hope you're getting it. Now, from an alternate standpoint, all I did again was I multiplied both sides of this equal sign by the denominator. Because we're going to get to the point where we need to see the change in theta, which will equal omega, which is the angular velocity, times the change in time. Hopefully you're still with me. Some more formulas for you. Kind of the same, but kind of different. Now in geometry, you know that arc length is 2 pi r theta over 360. Sometimes it's written 2 pi r times the fraction theta over 360. This measures the linear measurement of the circle's arc, or a part of it. But the problem is that that's in degrees. We don't want degrees anymore. We need radians, because that's what pre-calculus says we need. Our new arc length formula says pretty much the same thing, where we have S, arc length, is going to equal r, which is the radius, times theta. It's a lot easier. And it's a lot more helpful when we talk about angular velocity. And that is clearly going to be in radians. Because theta, radians, makes sense. Titan's a dog. He can't drive. But apparently, this is what happens when you give him some leeway on the computers. Let's try some examples together. Example 1 says Titan drove 60 miles per hour to the dog park. How far did he go in 20 seconds? Okay, So we need a couple of things here. A lot of these problems are going to be multi-step, multi-part. The first thing we want to do is we want to identify what kind of a problem this is. Well, if you remember from the first slide or second slide, miles per hour is a linear measurement. So I need linear velocity here the whole way. Now, the question is actually asking me to get to 20 seconds. So what I need to do first is I need to convert hours to seconds in this problem. This is dimensional analysis, a really fancy word for unit conversion. So let's do that first. My velocity is going to equal 60 miles over 1 hour, or 60 miles per hour. Now, because I'm trying to get to seconds, I'm really trying to just change the time measurement. The 60 miles is going to stay, because he didn't change how far he went or how fast he went. He's just changing the timing of it. So when hours are on the bottom, dimensional analysis says I have to put hours on top. Now, I like to go the whole way here. You might want to do a shortcut, and you'll see what I mean in a second. So if 1 hour is on bottom, 1 hour goes on top. The next conversion rate down, because I'm going from a larger measurement to a smaller one, is minutes. And 1 hour is 60 minutes. That's a 1-to-1 conversion. Nothing crazy there. We're not exactly where we want to be yet because we want to get to seconds. So minutes are on the bottom, minutes go on top. And if I have 1 minute, that conversion rate down is 60 seconds. Now with dimensional analysis, we are going to end up crossing out or canceling out units of measure only, not numbers. So hours divided by hours can completely cancel out. Minutes divided by minutes can also completely cancel out. And now I'm left with what I want, miles over seconds, because I want to know how far he went in 20 seconds. See where we're going? So we're going to multiply across, and then we're going to divide to get a nice easy number and see where we go from there. We're almost there. The second part of this problem is we have to represent what we want. This velocity or speed is 0.016 miles per 1 second, because that's what we have here when we simplify the fraction. But I don't want to know how far Titan went in 1 second. I want to know how far he went in 20 seconds. So if this represents 1 second, I'm simply going to multiply by 20. And when I do that, we're going to get our final value of 0.3 repeating, or 1/3. So Titan, if he drove 60 miles per hour to the dog park, which is really fast on this road, that means in 20 seconds, he went 0.3 distance, or 0.3 of a mile. Not bad. Moving on. Okay, the second example. This is actually way easier than you think it is. Example 2 says if a central angle spins 17 pi radians in 7 seconds, how fast is the angle spinning per second? Okay, so we need angular velocity here. Now, the formula is not super important to us right now because it is actually giving me a relationship that I need. And that ratio is going to be 17 pi over 7. Now, that's omega. And again, omega represents the angular velocity. So it is important to use the units of measure here. That's going to help us. So if omega equals 17 pi over 7, I actually want to find the decimal value of that because I'm trying to find out how fast is it going per second. So let's do that. Okay, so remember that this is in radians. And we know it's in radians because I have a pi there. Pi and radians go really well together. So when I multiply on the calculator 17 times pi divided by 7, I'm going to get about, and we'll round it to the hundredth place, 7.63 radians per second. I don't think I really had to write that out, but I felt like it because I like this marker. Moving on. Okay, example 3 is a multi-part problem. Now, we could ask you for both of them. We could ask you for one. I like both because we really need to convert both of them together, separately. Sure. Convert 80 revolutions per minute. First, let's convert it to radians per minute. So we need to know a couple of regular conversion rates here. So the first thing I need to do is I have to identify, well, how many radians are there in a minute? Well, if we go back to a previous video, we'll know that one revolution completely around is 360 degrees. But in terms of radians, 360 degrees is 2 pi radians. So I'm going to be multiplying this 80 RPM times 2 pi. So let's go ahead and do that. Is going to equal 80 revolutions over 1 minute. And we're going to multiply that by however many radians are in 1 revolution. And that's 2 pi radians over 1. We could say it's a revolution. Now, again, just like dimensional analysis, we're going to be crossing out units. And we're going to compare and multiply. The revolutions cancel out on both of them. Now I'm going to have what? 80 times 2 pi over 1 minute. That's going to be 160 pi. Now, what does that 160 pi represent? That represents radian measurements in 1 minute. Because again, think back to the problem. That's what I want. So what did we do here? I took a fraction of how many revolutions per minute I was given, 80. Then I multiplied it by however many radians happen in 1 revolution. Well, we know from the unit circle, and really from just talking about degrees to radians in general, I know that 1 complete way around a circle is 360 degrees, or 2 pi radians. Because I need to keep this in angular velocity, or an angular conversion, I've got to keep it in our pre-calculus terminology, omega and radians. That's our answer for the first problem. I know it's in part B. It's still the answer for part A. So I'm going to erase that, and we'll move on. OK. You might be more comfortable with working with linear velocity than angular. And that's fair. We've been doing linear velocity and linear speed and linear change for multiple years. This is probably your first year using angular velocity. So you should be happy to know that part B is all linear. Let's go ahead and work it out. First, I'm going to set up my problem with the same exact initial part, 80 revolutions per minute. Now I'm going to multiply that by our second part, which is the degree measurement of 1 revolution. Just like in the previous problem, we know that 360 degrees is 1 revolution. Now because I'm trying to get to degrees, I'm actually going to use the degrees, not radians. So we're going to do 360 degrees over 1 revolution. But we're not exactly done yet. I need one more fraction. The fraction we're going to use is converting time. Well, it said revolutions per minute. I want degrees per second. So not only am I converting from angular to linear, but I'm also converting a minute value to a second value. Well, we know that conversion rate. It's 1 to 1. We know that 1 minute is 60 seconds. Now I'm just going to cross out any units of measure that are in numerator and denominator and multiply out. OK, multiplying that out gives me 480. And that 480, looking at my phone, making sure that's right, is degrees per second. Final answer. Still with me? OK, for our fourth example, pretty simple. Maybe a drawing will help a little bit. So if I have my circle, and I know that the central angle is 70 degrees, we know a central angle has to be from the center of the circle, obviously. So that's probably 70 degrees. Man, I'm good. We know a radius is 8 centimeters. So I want to know what the length of the intercepted arc is. So I'm trying to find this distance here. Well, we can use an easier formula, which is the angular type formula for arc length. But the first thing I need to do is I need to convert that 70 degrees to radians, because it's not going to work otherwise. Let's get there. So the conversion for 70 degrees, I'm going to multiply by pi over 180. Well, multiplying that out will give me 70 pi over 180. But I can simplify that. This is going to end up being 7 pi over 18. That's the conversion to radians. Now let's plug in the rest of our formula. OK, well, 7 pi over 18 represents theta, the measurement of the angle. So all I need to do is multiply that by the radius, and we know that's 8. So what I'm going to do here is 8 times 7 pi over 18. Let's go the long way. 56 pi over 18. Let's simplify it further. 28 pi over 9. I can't go any further than that. Now, if I'm looking for the length of the arc, 28 pi over 9 is a little ugly. OK, so if we put this in the calculator and convert it to a decimal, I just realized you can't see that. I'm sorry. Thumbs up. OK, converting that to a decimal will give me about 9.77. and that's going to represent the length of the intercepted arc. Okay, lots to remember about this video. So to summarize it as quickly as possible, the thing to remember that is most important is the formulas. Understanding the formulas and understanding how to manipulate them is really, really critical for this type of stuff. Number 2, circular motion measures much differently than linear motion. And we're talking about radians. So again, linear motion, something I can measure straight. Angular motion, something that needs to be measured with a revolution or a circle or some kind of measurement that includes theta, omega, things like that. Radians versus degrees. Finally, a lot of these things are two-step problems. First, you would need to convert dimensional analysis-wise, and then you would have to convert one more time by entering things to a formula. See you next time.